Greetings I bid to our statistical physics professor, Dr. Fauzia binti Sulaiman. My name is Garrett, and my team members are Aina Fazlina, Muhammad Taufik, and Nur Hashima. We are from Group 4 and we will present our problem-based learning titled Crystals, Heat Capacity, Lattice Dynamics, Phonons, and Entropy of Black Holes.
Okay, for the problem statement for our project, a physics student found a crystal chunk being solved on a yard cell. As the crystal was shining radiantly under the sunlight, the student started to question the heat capacity capabilities, its lattice dynamics, the phonon dispersion phenomena, and how it related to the entropy of black holes. As a physicist, how would this student be able to have knowledge on this curious phenomenon? Next. So for the objectives, first, to investigate the theory of lattice dynamics in crystals, to investigate the theory of heat capacity of crystals, to investigate the phonon dispersion phenomenon in crystals, to relate the concept of the entropy of black holes to crystals.
A crystal structure is characterized by its unit cell, small imaginary box containing one or more atoms in a specific arrangement. The unit cells are stacked in three-dimensional space to form the crystal. The symmetry of a crystal is constrained by the requirement that the unit cells stack perfectly with no gaps. There are 219 possible crystal symmetries called crystallographic space group. These are grouped into 7 crystal systems, such as cubic crystal system or hexagonal crystal system. Next is methodology. This is our methodology for completing our PBL mini project. Lattice dynamics. Lattice is the study of the vibrations of the atoms in a crystal. We already know that atoms must be vibrating within crystal because it is the natural interpretation of temperature. Although traditional crystallography often shows image of atoms being kept in static position through stiff chemical bonds, yet crystallographic measurement prove that atoms can be vibrating with an amplitude that can be 10% of an interatomic distance. And because of that, we need to understand lattice dynamics in order to have complete picture of crystalline materials and amorphous material. For the application, example of application of lattice dynamics such as propagation of sound waves in crystal and interaction of materials with light. For example, the absorption of certain frequency in the infrared spectral region is directly to the existence of specific lattice dynamic motion. Other than that, lattice dynamics also gives us properties such as thermodynamics, superconductivity, phase transitions, thermal conductivity, and thermal expansion. Atomic motion in lattice dynamics are described as harmonic traveling waves. Each wave can be characterized in terms of its wavelength, lambda, angular frequency, amplitude, and direction to travel. Wavelength can be defined as vector k, vector parallel to the direction of propagation of the wave.
Now let's move on to the heat capacity of crystalline solids. Any theory used to calculate lattice vibration heat capacities of crystalline solids must explain two things. Number 1. Near room temperature, the heat capacity of most solids is around 3 K per atom. The molar heat capacity for a solid consisting of n atom molecules is approximately 3 nr. At low temperatures, Cv decreases, becoming 0 at T equals 0. Heat capacities have a temperature dependence of the form A3 powered by 3 plus gamma T, where the T powered by 3 term arises from lattice vibrations and the linear term from conduction electrons. Classical mechanics would predict that Cv equals 3R at all temperatures, in violation of both experiment and the third law of thermodynamics. Kinetic and potential energy of atoms in a crystal. Atoms can vibrate in one of the three directions and have both kinetic and potential energies. During an oscillation, the energy alternates between each type. Depending on the local arrangement of atoms in a crystal lattice, the potential energy interactions can vary in the x, y, and z directions. The kinetic energy affects the shape of the harmonic potential. Observing the figure, we can see that when the energy is lower, the displacement is larger. Similarly, when the energy is higher, the displacement is smaller. Dulong-Petit law for high temperature molar heat capacity. At temperatures where all 6 vibrational degrees of freedom are accessible in a crystal of a single element, for example copper, the molar heat capacity C-mol is given as. This is called the Dulong-Petit law. Surprisingly, heat capacity does not depend on crystal structure nor on bonding. Unlike in gases, in solids, Cv is only slightly smaller than Cp. Remember that the mass of one mole depends on the molar mass of an element, which increases with the atomic number. At 298 K, most solid elements have a C of about 3R. Observing the prediction of the law of Dulong and Petit, we can see that the Cp is equal to 24.94 joules per K per mole. So what if the crystal has more than one element? In this example, 1 mole of potassium chloride contains 2 Na atoms in total. Compared to 1 mole of pure potassium, there are twice as many atoms contributing to the heat capacity. Looking at the figure, the basis consists of a chloride ion, which is denoted as large green at 000, and a potassium ion, which is denoted as small blue at 1/200. If there are two elements in a compound, the C-mol is approximately 6R. For example, sodium chloride. The C-mol of sodium chloride is at 51 joules per mole per K. If there are 3 elements or atoms in a compound, each mole will have 3 Na atoms, which gives you C-mol approximately 9R. For example, potassium difluoride, the C-mol is at 72 joules per mole per K. Okay, so let's take a look at the heat capacity of solids in the limit of low temperature. Einstein treated each atom on a lattice in a solid as an independent oscillator with a frequency of F0. Einstein predicted that at thermal energies kT is less than HF0, some vibrational energy states are not accessible. He derived an equation to describe the thermal activation of the energy of the oscillators as shown below. This equation predicts that T is at 0K and the second term is at 0. In the limit when KT is more than HF0, however, the second term will increase towards KT. After that, the amplitude of vibrations are quantized. Energy of the vibrations will then take on quantized values. We can see that the energies are quantized in the case of lower mass, higher mass, and a higher. Here is an example for when Einstein's theory is applied to C for copper. The theory successfully predicts that the heat capacity is lower at low temperatures, as some vibrational states are not accessible. Observing the fit of the data at the lower end of the graph, The Einstein's theory is not very good at very low temperatures.
Okay. All right. Next, we continue on to phonon. The term phonon are usually used to show crystal vibration. It can be regarded as a particle that can interact with both holes and electrons. Next. The band structure of a solid material depends on the location of the lattice. Crystal vibration, which we know as phonon, will be transformed into reciprocal space, causing the band structure to vibrate, and the vibration will interact with electron in a strong way. The interaction between an electron and a phonon can be described in terms of transition rates between one state to another state in the reciprocal space. The transition state can be defined through dividing the rate of number transition from an initial to final state, final rate that will take place over time. The typical scattering rate is around 10 to 100 scattering per picosecond. The input data for the calculation is called deformation potential and the phonon dispersion relation. As we know, a phonon is a wave-like displacement. The vibration is represented as wave with a frequency. The amplitude of waves in this are quantized. Only discrete values are taken for the energy.
Moving on to the next discussion, which is relation between crystal and entropy of black hole. Referring to the figure, this is the entropy visualization of black hole. During this case, the crystallized lattice structure of water molecules demonstrates minimal entropy. However, when the ice block is exposed to heat as a function of time, the intermolecular forces are broken, separating the molecules and consequently creating a liquid. The observable universe showcases the chaos and brutality that may happen when systems exist over time. The universe has an inherently high level of entropy as well. Everything in our universe, from the micro to macro, is bent and mankind. Next, what entropy actually measures is the number of possible arrangements of the state of a system. So, the interaction without releasing energy leads to dark character of the figure shown. When the neighboring particles share the same structure, can refer to figure B, they are in resonance. The neighbor particles in a shell should have the same structure. The particles do not bind together with strong force. They form perfect crystal layer with no friction between layers. So in figure A shows the single particle of black hole and figure B shows the crystal planes are parallel to the surface of the black hole. Next. Topologically, octahedron particle form sphere can refer to figure C has two poles. An octahedron on the sphere has one axis vertical to the sphere, one axis along longitude, and one axis along latitude. The longitude effects are less within the areas near the poles. The particles are mainly aligned with the axis of the region, and therefore the other two axes are aligned by external forces and form an ideal crystal. For one part can refer to figure D, it is both cross-shaped, bright arms, and circular features. Next. In part system can refer to figure E, the middle pole areas may have ideal crystal surrounded by other cones which are directly mapped to the intense spots within the real image in figure E on the right side. Due to gravity, photons released from the dipole surface are redshifted, while photons from the upper level of region are blue, which is less redshifted. For the last point, when there is an excretion disk, circling matter will touch the surface of part, where the vibration movements along a longitude convert the circling matter into layers of spheres wrapping round the region. The newly formed spheres twist upwards. When these particles reach a pole, they are accelerated by outgoing part energy of the poles. The particles are continuously pulled into the new sphere from the rotating disk and ejected at the highest of pole. This dynamic process forms a part jet, can refer to figure F, black hole jet. So this is how the crystal be related with entropy of black hole in terms of black hole production.
Okay, so now let's look at the Phyla table. Facts. The student sees the crystal in the yard sale under the sun and wonders how much energy is being absorbed to raise the temperature of the crystal by 1 degree Celsius. So how will the student calculate the heat capacity of the crystal in the yard sale? The idea is that since each crystal is structured differently, the value of C will be different for individual crystals. Using the heat capacity formula can be a great help in finding the heat capacity of the crystal. We can also use Einstein's theory to explain for the value of C in crystals. So what we can learn from this is that it is not quite possible to decide that one crystal's heat capacity is the same with another. Therefore, we would need to carry out experiments to determine the heat capacity of individual crystals. So what can we do? The action plan is to gather the necessary apparatus for a calorimetry experiment. We need to measure and or calculate the mass, heat energy, and the temperature change during the experiment. And then we would compute those values into the heat capacity formula to get the value of heat capacity for the crystal, which is C equals to the change the change in heat energy over mass times the change in temperature.
Vibration of atom at an equilibrium point in solid always happen at any temperature. This vibration yields information about the thermal properties of solid, such as specific heat and thermal conductivity. Ideas. Lattice is a regular arrangement of atoms which are joined together by elastic spring. Consider a one-dimensional chain of atoms where each atom has mass m and is attached to other atoms by massless spring where A is distance between atoms. Learning issue: difficulty to imagine the one-dimensional chains of atoms where the atoms are attached by massless spring. Action plan is to review the one-dimensional atom model attached here. From the figure, the sphere here symbolizes this atom, while the spring symbolizes the force in between. The force exerted by a spring of an atom is given by F equals to negative beta times x, where beta is the spring constant. The periodic is P equals to 2 pi square root of m over beta.
Next on the Phyla table, phonons are usually referred as the crystal vibration. Phonon can be regarded as a particle that can interact both holes and electrons in the crystal. For ideas, band structure of a solid material, which in this case is a crystal, will depend on the location of the lattice. The vibration will happen as the phonon transforms into a reciprocal space. Vibration happens as the phonon transforms into a reciprocal space mode to interact differently with the electrons. For the learning issue, it is to find the transition rate between one state to another in the reciprocal space. For action plan, to study the different types of vibration that can affect the band structure. Other than that, calculating the transition state that is given by different band structure. The formula for transition state used is rate, the rate of number of transition from an initial KO to final KO that will take place over time.
So the next part of Villa table, for facts, the crystal incorporates a regard to micro black holes physics, where derive a brand new mass temperature relation for Schwarzschild micro black holes. Change of entropy equals to change of energy divided by temperature. For ideas, find the law of production of crystal black hole. Calculating the dark particle structure of black hole. For the learning issue, difficulty to imagine how the micro black hole affect the production of crystal. And for action plan, understand how the black hole occur. Understand the relation between black hole and crystal in terms of the entropy. So for the formula to calculate the dark particle structure of black hole is 3 times 2n times 137 to the power of 2m minus 1. In conclusion, there are a lot of interesting physical phenomena that we can learn from studying crystals. The lattice dynamics is functioned as an absorption of certain frequencies in the infrared spectral region is directly from the existence of specific lattice dynamics motions. The heat capacity of crystal can be calculated and explained with Einstein's theory of heat capacity. Phonon in crystal usually refers to the crystal vibration and can be regarded as particles that can interact with holes and electrons. The crystal incorporates a regard to micro black holes physics, where derive a brand new mass temperature relation for Schwarzschild micro black holes.
And that is all from us. These are the reference lists used in this presentation. Once again, we would like to thank each and every one of you for viewing this video presentation. Thank you.